Slope measures the steepness of a line. It represents a rate of change. That's super important. From math, we know that rate of change is rise over run. So the slope, okay, is given the letter m, which is change in y over change in x. Okay, and so if we have a line of constant slope, the steps are equal. So this is a line that has constant slope because the rate of change of the x between each rate of change of y between the same rate of change in x would be equal. So how do we calculate? So let's have an example here. If we have a position time graph and we have these 3 points right here, and then we draw a straight line through them, so we can calculate the slope, which would be rise over run. Now, what would that give us? Well, the rise here, the variable is x, so the rise will be delta x, and the run, the variable is time, would be delta t. But delta x over delta t is velocity. So what we get is the slope of a position time graph gives us the velocity. Okay, if we have a negative slope like that, okay, so negative slope would give us negative velocity. And if the slope was steeper, maybe something like that, so steeper slope gives us, or means, greater speed. Okay, so let's use this as an example to find the velocity here. So as an example, now we can use 2 points. So using the point 3 and 15, so that would be this point right here, and 1 and 5, which is this point here. Okay, so Vx is change in x over change in time, which is xf minus xi over tf minus ti. So Vx is equal to, okay, final position is 15, initial position was 5, and the time interval was 3 minus 1. So this gives us a velocity of 5 meters per second, and it's positive 5 meters per second, so it's to the right. Okay, so in this case, it was kind of easy to figure out the velocities by just using the slope rise over run formula. But we got lucky in this case because all the points were on this line up here. Okay, but in reality, again, like we talked, that's uniform motion. But in reality, we won't get that. We're not going to get all the points on the same line. So, here's a more realistic example of how our position time graph could look like. And so it's up to us to choose or to draw a line of best fit through these points. Okay, so with your ruler, what you want to do is pick a line that best represents these data points. We already have some experience doing that. Draw our line, and that could be our line of best fit. So if we ask what is the velocity at time is equal to 2 seconds, we could use the time interval 0, so between here and 3 seconds right there, to calculate what the velocity is at this time right here. Because we have all these points around time is equal to 2, this would give us a pretty good average. So we can use the points 0, 0, and 320. Okay, so notice how this point maybe was a little bit higher, but so we're using 3 and 20. We need to use points on the line of best fit. And so if we calculate the V average here, V average, that would be 20 minus 0 divided by 3 minus 0. Okay, so we get an average velocity of 6.7 meters per second. Now that doesn't mean that the velocity at time is equal to 2 is 6.7 meters per second. It is the average velocity between 0 and 3 seconds. Okay, so that will give us a good estimate. But what we could do, we could zoom in to this time. So if we want to figure out what the time is at this point here, instead of using 0 and 3 seconds, we can zoom. We can go a little bit closer. We can go 1.5 and 2.5. So we're going to be using this point here, and perhaps this point here. So our line of best fit through those 3 points would look a little bit like that. Okay, and because the time interval is closer to 2 seconds, this could give us a more accurate picture of what the actual velocity is at that point. So in this case, we might use 1.5 and 11, and the other point that we could use is 2.5 and 15. If we calculate the average using these 2 points, we get 4 meters per second. Okay, notice how it's different than this. Okay, so this slope is smaller than the bigger slope. Okay, and and because the time is closer to 2 seconds, that might give us a more accurate description of what the actual velocity was at 2 seconds. Now we can continue doing this forever, right? We can zoom in even more. So at 2 seconds, the curve could look like this, and if we pick the tangent or super close point, we get what we call a tangent. And a tangent is a line that touches a point at only one that touches the curve at only one point. And essentially what we're doing, it's just not super easy to understand at the first time, but what we're doing is we're going closer and closer to 2 seconds and calculating the slope that way. So what we're having is a very small time interval. Okay, notice how it's getting, here was 3 seconds, and this was 1 second, and this is 0.02 seconds. So we're going smaller and smaller, and the closer you go is you get to what we call a tangent. So tangent at 2 seconds. Okay, and if we make that time interval infinitely small, we get what we call instantaneous velocity. Okay, so the tangent at a point is called its instantaneous velocity. And then we can do the same thing with acceleration. If we have a velocity time graph and we look at the slope of this line, well, the rise is meters per second, the unit of the run is second, and which would be meters per second squared, and we know that's acceleration. Okay, so the slope of a velocity time graph gives us the acceleration. And just like we had with the position time graph, if we have a negative slope, that gives us a negative acceleration. And if we have a large slope, this gives us a large acceleration. Okay, so again, another example, we could use the points 0, 0 and 2, 10. And the acceleration x is equal to v final minus v initial over t final minus t initial. And so we have acceleration x is equal to 10 minus 0 over 2 minus 0, which is 5 meters per second squared. Okay, so that would be how we would calculate acceleration from that slope. And so as a model problem, we can analyze the following position time graph and sketch the velocity time graph of the same data. So this would be our velocity time. Well, here we have uniform motion for the first 10 seconds. We can calculate the slope. So Vx at that point would be, we can use this point and this point, which would be 10 minus 0 over 10 minus 0. So that would give us 1 meters per second for the first 10 seconds. So if we had 5, 10, we would be going at 1 meters per second for the first 10 seconds. Then over here we have a slope of 0. It's a flat line. So for the next 5 seconds up to 15, we would jump down to 0. And over here we would have negative velocity because we have negative slope. So to calculate the velocity there, we would have Vx final is 0 minus initial of 10 divided by final time of 20 minus 15. Okay, so this was good, negative 10 over 5, which would give us negative 2 meters per second. So in this case, we have negative 1, negative 2 meters per second. And so we would have a constant negative velocity of -2.